Hello everyone, welcome to my video. In this video, we're talking about example 6/25, which is one example in the general motion of equations. Here we have a 1800 kilogram, a rear wheel drive car accelerates forward at a rate of half of the gravity. If the modulus of each of the rear and front springs is 35 kilonewtons per meter, we want to estimate the resulting momentary nose-up pitch angle theta. Okay, and we'll begin by assuming a rigid body vehicle here. Okay, so we're no longer looking at a car as a point. In this case, we'll have to look at one component at each time. Now think about it. You want to find the angle here, and where does the angle coming from? Where does it come from? Okay, now think about this car here, right? When the car starts to accelerate, right, at a small instant, and it accelerates from the back, so it's being pushed like this. So there will be a small angle. Now I'm making this intentionally big here. There will be a small angle the car is making when it starts to accelerate, right? And as the question said, this upward pitch angle during acceleration is called squat. At the same time, and if there is a downward pitch angle during the braking, right, like this is called dive. In this case, we're trying to find this angle here, the squat angle. Now, looking at here, the car and the two set of spring here. When there is an angle, that means the spring at the back and the spring at the front, they have to deform. But deform how? Compress or stretch? Think about this. If this is a horizontal, when nothing happens when the car is at rest, when the car starts to accelerate, the nose goes up, what happened here? This spring is being compressed, and this spring is being stretched. If we want to find the angle here, if we can find out based on the spring, how much does the spring stretch, how much does the spring compress, we can find out based on Hooke's law, F spring equals to 1/2 kx squared, or k delta x squared. If we can find that delta x, we can find the angle. See? This is where we want to do. This is where we're going here. Okay, so as always, given that, keep in mind, we'll start with what's given to us. 1800 kilogram. Acceleration is g over 2. We'll just do a simple quick calculation here when we're writing down those simple numbers here. And k is 35,000 Newton per meter. And when it at rest, the force is being shared equally front and rear. Right, we'll do the calculation later. But think about when the car starts to accelerate, how would you draw the free body diagram at that instant? Okay, so we want a free body diagram. So at the instant of accelerating, when you start to accelerate. Okay, we'll do the free body diagram here. G and EF method still holds. Gravity has to be here. And the normal force given by the rear wheel and front wheel, NB. External force, the force F that is driving the car forward, because this is a rear wheel drive car. Where do we draw this force? Okay, we don't want to just draw this in the center, or in this question, if you draw this in the center, it does not really make a huge difference. But in this case, we want to draw the force right here. this is the force given by the rear wheel. Okay, or if you want to simplify it further, in this case it doesn't really matter. We can just think about this force is right here at point A. I know there is some simplification here, right? But for this kind of question, you can safely assume this force is right at the same point A, where the point A is having the normal force. Okay, do we have any G and EF, the external force? Finally, the friction. Do we have any friction? Well, two reasons. Number one, the friction is not given in this question. There's no friction coefficient given to us. And number two, we are looking at this particular instant. So in this case, friction is not is assumed to be not exist. So we have no friction here. So this is our free body diagram. At the same time, if you recall from the video, other than free body diagram, now we have an extra diagram that we can use. It's called the kinetics diagram. The kinetic diagram tells us where is your acceleration. Or in this case, think about Newton's second law. F equals to ma. F is comes from your free body diagram. Then ma is a kinetic part. In this case, our ma is right here. Your acceleration of the car, ma, or the equivalent to the force. Like all resultant force give you this ma. So based on all these force analysis, we can write sum of Fy equal to 0. Oh, I forgot to define them. So this is my y, this is my x, and counterclockwise as positive as always. And sum of moment about any point give me MAD. Now, it comes to where do you choose that point? Okay, remember, you can choose any point on the object or even any point off the object and make all forces make a moment about that point. Now, the thing is, you want to simplify your calculation as much as possible. So the choice of the point it will determine whether you're going to suffer a very long, complicated mathematical calculation or a very simple one. Now in this case, I want to choose point A because point A has two forces going through, right? So then this NA and F won't make any moment about point A. That's the reason I'm choosing point A here. Now, let's replace everything. Sum of Fy, we have NA, MB, and MG. NA plus MB minus MG equal to 0. And then sum of MA, all forces making the moment about A, we have the gravity making a clockwise moment. Now it is negative mg times 1.5 and comes from here. 1500 millimeter, which is 1.5 meter. And then we have the NB is making a counterclockwise moment plus MB times 3. Again, the 3 comes from the 1500 times 2 meters, or 2000 millimeter, equals to the MAD. Remember, this MA is the moment, the force, the resultant force of the vehicle. Okay, think about this. In this case, everything considered, eventually, where does this car go? Go forward, right? So this is your resultant force, give you this MA. And this MA is applied directly on the center of gravity. So we are looking at how is this force MA is making a moment about point A. First of all, it is clockwise, so it will be a negative. Then how far? What is the moment arm in this case? Okay, think about this, looking at it. This is our moment arm. In this case, 600 millimeter, which is 0.6. And negative MA times 0.6. Your A is calculated at the beginning, 4.905 meter per second square. Now, two equations, two unknowns, NA and NB. You know M, you know G, you know A. We'll calculate NA and NB. NA and NB. NA, 7063.2 Newton, and NB, 10,594.8 Newton. This is your NA and NB. This is your NA and NB at the moment when your car starts to accelerate, when you already tilted. I remember when you tilt it this way, what do they feel? Let me use a different color here. When you're tilted, when your nose is up, the back spring or the rear spring is feeling being compressed, and while your front spring is being stretched, right? This is how your car is going to tilt, have the nose up effect. So think about the force the spring's having. This spring is being compressed by a delta N, and this force is being stretched by delta N. And this delta N is the difference between when the car is at rest versus when the car has a nose up. And they are the same because this is a perfectly symmetrical situation. Your mass center is in the middle, right? So whatever you compress at the back will be the same amount you stretch at the front. If these two forces is the two force of NA and NB at the moment when the car has a nose up, what about we compare these two forces with the two forces NA and NB when the car is at rest? Right? Then we can take the force difference, and the force difference delta N would have to equal to 1/2 K delta X squared. Right? Your delta N, this is where they are connecting. Your delta N has a connection with delta X, with how much your car, the spring of the car, is going to deform or has deformed. Okay, so now take a look at rest. At rest, what do we have? Well, at rest, your two forces are being equal, NA and NB, and they equally sharing the force of the given by the entire gravity, entire weight of the car. Right, so we'll just call this NA prime and NB prime. The two forces at rest, the two normal forces at rest, giving to the rear wheel and the front wheel, is the weight over 2, 8829 Newton. Okay, let's calculate the delta N here. The delta N is the same as either you use NA minus NA prime, or you use NB minus NB prime. Note I'm using a absolute value here because one is stretched, one is compressed. There will be different signs. So I'm using the absolute value here. The absolute value gives us the difference, the absolute difference is 1765.8 Newton. So this is a delta N, the force either compressing the spring or stretching the spring, the same force. So this is a front or back? Front or back. Now for each spring, remember, you have a set of spring or two springs for the rear and two springs for the front. Remember, it's a car, right? It's a real car, not a cartoon car. You have 4 wheels, 2 wheels at back and 2 wheels at front. That means for each spring, what is the force on each spring? This is for the front set and back set. Then for the front per one spring, you need to divide it by 2 again. Right, remember, let's go back here. Right, you have 2 wheels. This is two springs together giving you this force. So you need to divide it by 2 to have 2 wheels. 2 wheels at the back and 2 wheels at the front. Now, for each spring, your Fs, the force on the spring, is the 1765.8 divided by 2 again. 882.9 Newton. Remember, you have 2 wheels per set of the spring. So per spring, you need to divide by 2. Again, according to Hooke's law, your Fs is K delta x. Your delta x is therefore 0.0252 meter, or how much? 25.2 millimeters. So compared to a car, this deformation is very small. Okay, now let's find out the angle here. Okay, we started with A and B, right, and the center at G. Right, this is where we started. And when we accelerate, I'm going to exaggerate here. So this is your, let's do this. This is your A and B, okay? And each is 1500 millimeter, front and back. And then this is how much your delta x is. Okay, it's the same amount of delta x if you draw it here. This is also delta x. Okay, delta x, delta x. And your delta x you calculated is 25.2 millimeter. Right angle triangle, 1500, 25.2. So your theta equals to sine inverse 25.2 over 1500. 0.96 degree. Okay, again, as I said, I'm exaggerating here. So it's the angle is very, very small, right? Nearly impossible to be seen by bare eyes. Maybe you can feel it, but it'll be hard to see. Okay? And that's it. Thank you for watching. I'll see you next time.